Okay, welcome to the second part of the calculus class, and let's start the example 4. Okay, so here is the example 4. So question is, the problem is to find the derivative of a function f at some point, say 2, or some arbitrary, no, arbitrary point A. So if I first consider the case when x is 2, then we can just evaluate the previous formula at 2. So as h equals to 0, f of 2 plus h minus f of 2 over h. That should be evaluated. So in case of f2 plus h, you need to plug in 2 plus h into this x in f of x. Then you get this. And if I evaluate f at 2, you get negative 3. So this is f2 plus h, and this negative 3 is f of 2. If you expand this term, and then if you combine, say, 4h with negative 8h, then you get negative 4h. And then if you cancel the constant term, I mean 4 minus 16 plus 9 minus 3, then the numerator becomes h squared minus 4h only. And then if we look at this numerator, each term has h in common, so I can rewrite the numerator as h times h minus 4, and denominator is h, and I'm letting h go to 0. Now this h goes to 0 as h approaches 0. Okay, now at that point h does not become 0. So at this point we does not consider the case when h is 0, meaning, so this implies h minus, so we have this, yeah, h is not 0, so I can cancel this term. Then you have only h minus 4, and then if I let h go to 0, the limited value will be negative 4. So that is so this negative 4 is the derivative of this function, derivative of f, so at 2, or you may say that is the slope of the tangent line of this function at this point 2, or you might say that at point 2 and negative 3 point. Okay, and either is fine. So that is the slope of the tangent line of the given function when x has the value 2. Okay. Now in problem B, we want to find the expression for this derivative at some arbitrary point A. So I want to plug in a plus h and a in the definition. Now please be careful when you expand a plus h squared minus a times a plus h plus 9. And f of a is also a polynomial in a. So if you expand all these terms, this is what you get. Now, as you can see, a squared will be cancelled. Okay, and the constant term in h will be negative 8a plus 9 plus 8a and minus 9. So plus 9 and minus 9 will be cancelled, and negative 8a and plus 8a will be cancelled. So what remains will be 2ah plus h squared minus 8a in the numerator. And here, similarly to the previous case, h is common. So I can rewrite the numerator by h times 2a plus h minus 8. So h in the numerator and h in the denominator can be cancelled to produce this polynomial. So if I plug in 0 in h, you get 2a minus 8. And that is the derivative of this function at a, or that will be the slope of the tangent line when x is a. And the result in part A is a special case of this, because if I plug in 2 for A, then 2 times 2 minus 8 will be negative 4, and that was the answer in part A, and so that is a very special case. But in part B, we are considering some general situation. So we define the tangent line to the curve at the point P to be the line that passes through the P and has the slope m given by the equation 1 or 2. And since this is the same as the derivative, which is denoted by f prime of a, so we may say this f prime a is the slope of the tangent line. Okay, so if I use this f prime over a, then the tangent line has the equation will be y minus f of a equals to the slope m. Now that m can be replaced by f prime of a times x minus a, or y equals to f prime of a times x minus a plus f of a will be the equation of the tangent line, okay, when x is a, or when a and f of a is given. So as I said, this is the equation of the tangent line. Okay. Now, suppose y is a quantity that depends on another quantity x. Thus, y is a function of x, and in that case, in math, we use this expression, y is a function of x. So that means when x varies, the corresponding function value changes. So if x changes from one value, say x1, to another value, x2, the change in x will be denoted by usually this symbol, delta x. So delta x represents the change in x value. So if x changes from x1 to x2, then delta x is defined by x2 minus x1. So this is representing the change in x. And this change in x is sometimes called the increment of x, even though the x value may decrease. So even in that case, we just call this delta x sometimes delta x by increment of x. So when x changes from x1 to x2, then when x is x1, the function value will be f of x1. When x is x2, the function value will be f of x2. So when x changes from x1 to x2, then the corresponding change in y will be f of x2 minus f of x1. So that is denoted by usually delta y. So this is the change in the y variable. So this is the difference between these two, delta y over delta x. which is f of x2 minus f of x1 over x2 minus x1, that value is called the average rate of change of this function y with respect to x. Okay, so that is called the average rate of change of y with respect to x. Okay, so what does that mean in the graph of the function? So my point, my function, my x value was at x1 initially. So when x is x1, so on the graph of the function, so this black curve represents the graph of the function. Okay. Now, when x is x1, you are at some point, say P. When x is x2, you arrive at Q point, Q of x2 and f of x2. So as x varies from exchanges from x1 to x2, the corresponding y value changes from y1, which is f of x1, to y2, which is f of x2. That means the point on the curve is changing from this point P to Q point. So at that point, the delta y over delta x, the average rate of change, represents, so delta x is the difference in x values, and delta y represents the difference in y values. So if I divide the delta y delta x in figure 8, that average rate just represents the slope. Slope of this secant line passing through these 2 points P and Q. So the average rate of change represents just the slope of the slope of the secant line PQ. Okay, so this is the slope of the secant line. Okay, so that slope of the secant line will be, from now on, that will be called the average rate of change of y with respect to x over some interval from x1 to x2. So that's what people in engineering or economics prefer. Okay. Now, as x approaches, now in this figure, as x2 approaches x1, so as x2 approaches x1, then this slope. So previously we used m sub pq to denote that slope, right? And then as x2 approaches x1, so if I consider this a limit, then m sub pq, or that was the limit of delta y over delta x as x2 approaches x1, then if that limit exists, then that was representing the slope of the tangent line at P, at x1, right? And that slope of the tangent line was, in the previous slide, was denoted by f prime at x1. Okay? Please remember that notation. So that was the derivative of the function at x1. And if this limit exists, then this limit will be called the instantaneous rate of change of this function with respect to x at x1. Okay? So simply we say that is the instantaneous rate of change of the function at x1. Okay? So instantaneous rate of change of this function is the limit of this expression, or in other words, limit of delta y over delta x as x2 approaches x1. In other words, the delta x goes to 0. And as I said, that if that limit exists in the previous slide, we called in math as the derivative of f prime at x1. But in some other fields of sciences, people may want to call that value by the instantaneous rate of change of the function at a point. So in our calculus class, f prime of x1 may be used for the notation. Graphically, that represents the slope of the tangent line. So this slope of the tangent line is the meaning of this limit in graph of f of x. And in some applications, that was representing the instantaneous rate of change of the function at the given point x1. Okay, so you need to understand all three. So limit of f of a plus h minus f of a over h as h goes to 0, or you may say limit of f of x minus f of a over x minus a, and then if you let x goes to a, or sometimes we may consider delta x, and then you let delta x go to 0, and we are considering the limit of delta y over delta x. Okay, here delta y denotes the change in function value, while delta x denotes the change in the x values. So these all three limits, if one limit exists, then all the other will exist, right? And that if the limit exists graphically, that was representing the slope of the tangent line of f at point a and f of a, or as I said, at this point. And in the symbolically, we used f prime at a, and we called this guy as the derivative of f at a. And now we have the new name as the limit of the average rate of change. So this was called the average rate of change of f over from a to a plus h. Now we will call that the limited value will be called the instantaneous rate of change of this function at this point A. So the same value, the same limited value may be called may be used may represent this slope of the tangent line when we talk about the graph of a function, Or in math, in many cases, we will represent the limit as f prime of certain function at certain point. And if you measure the rate of change of certain function, especially in some application fields, that limit is called the instantaneous rate of change. Okay, so that measures how fast the function changes at a given point. So one limited value can be expressed under different names or expressions. So please remember all these equivalent relations. Okay. So if I consider this secant line, as I mentioned, the secant line is a line that intersects the graph at two distinct points. And then if you let this Q approach this P, or you may say if Q has the x coordinate of A, and if Q has a x coordinate of A plus H, then that means the change in 2x value will be H, and we are using delta x to denote that difference. The corresponding y values, okay, f of A and f of A plus H, the difference between these two is denoted by delta y. Okay, and this delta y over delta x, the limit of this ratio, first of all, delta y over delta x measures the average change of the function. And then if you reduce the step size, and I mean, if you let the step size approach the value 0, and if the limit exists, the limit may not exist, right? But if the limit exists, then that will be denoted by f prime at A, or that will represent the limit of the average rate of change. So that is called the instantaneous rate of change of the function. So please be familiar with this, and you need to remember, okay, this slide. Okay, so sometimes I will use just the derivative of a certain function at a certain point, but sometimes I will call that value under the instantaneous rate of change, and then I will measure the rate of change of the function at a point. Okay, so this f prime at A measures the instantaneous rate of change, the rate of t, right? So some extreme value of the average rate of change. So as an example, what if I consider some constant value, say 2? So I'm just defining a constant value. So constant function is considered. So for every x, the value of the function is 2. Okay? So the graph will be like this. Then when you consider A and A plus H, A and A plus H have the same function values of 2. So the average rate of change of this constant function will be always 0, right? So in that case, fa plus h minus f of a will be 0 for all a. For every a, f of a plus h minus f of a will be 0. So delta y is 0, right? So the limit value will be, so limit of delta y, so this is a delta y. So the limit of delta y over delta x will be 0, for every a. And this limit is f prime at a. So in case of a constant function, the instantaneous rate of change of that constant function at every point will be 0. Or in other words, the derivative of this constant function at every point a will be 0. Questions? Okay. Now, so far, so in the up to this slide, up to section 7 in chapter 2, we considered several functions and some limits and some f prime, the derivatives of some functions at some point. Okay. So far, we considered the derivative of a function at some number, at some point, say a. Here, we want to change our viewpoint, and we want to let this number a vary. In other words, I want to interpret a as a variable, not a fixed number, but some variable x. So if I plug in x to the right-hand side of this expression, fx plus h minus f of x over h, and then you let h go to 0. If that limit exists, okay, then I have f prime of x. So in other words, I'm just considering certain function, certain mapping. So if that limit exists, then I want to assign that limited value as the value of certain function denoted by f prime of x. Okay? So from now on, I want to have some freedom in the variable a so that it can take any value. So given any number x which this limit exists, we assign to x this limited value f prime of x so that we can regard f prime as a new function. And this new function, it will be called just a derivative of f. Okay. So we know that this f prime at x, in other words, f prime of x can be interpreted as the slope of the tangent line of the function f at this given point. And this f prime is called the derivative because it has been derived from f by some limiting operation. And then this is a new function, and the domain of the f prime will be the set of all the x values, such that f prime of x exists. So as long as f prime exists, then that x will be regarded as the domain of f, in the domain of f prime. Of course, even though I just said this one, that this x must be in the domain of f such that f prime of x exists. That's what I mean. Okay? So if you consider some function, say x squared, okay, let me consider the special case, the previous example, the constant function. So for this function, moments ago, I told you, I showed that the derivative of f exists at every number, right? And this constant function has whole real line as the domain. So in that case, the domain of f will be the whole real line from negative infinity to real line, the plus infinity. Then, so the domain of f prime will be the same in that case. Okay? So that is an example of the domain of f prime. Now, depending on the situation or application, sometimes people instead of f prime of x, sometimes people use y prime to denote the derivative of a function at x. Sometimes dy dx may be used. Sometimes df dx may be used. So here f is the name of the function. Okay, and if y denotes this f of x, then dy dx or df dx, or sometimes d dx times f of x may be used. So those are very common notations. Now, in some rare case, you may use the uppercase D to denote the derivative. So uppercase D of f of x, or sometimes we put this subscript x, okay, for D, so that I'm just to imply the differentiation in x variable. So these two notation may appear especially in physics or engineering textbooks. But anyway, they are all representing the same function, f prime of x. And this uppercase D or ddx, these symbols are called the differentiation operators. Okay, so we will talk about these operators. The exact meaning of the operator is a little bit beyond the scope of our class. But anyway, so you don't have to know the exact meaning of the operator. But anyway, so we will call this uppercase D or ddx as the differentiation operators. So these are some notations representing f prime. So for example, when say sine function is given, sometimes sine prime of x may be considered, may be used, or sometimes y prime may be used to denote the derivative of sine function, or sometimes we use ddx of a sine function, or sometimes d of sine function. So they are representing or the differentiation, the derivatives of the sine functions. Okay. These are just notations. Okay, so this is just a background, so you can read this slide yourself. Now, when I consider f prime at a, then that represents the derivative of f at a, right? And that is symbolically. So what is the meaning of this? You consider the derivative of f at a, meaning you are considering the limit of f a plus h minus f of a over h, and then you will let h go to 0, right? Or you may say, so instead of calculating this, you can find f prime of x, the derivative of the function. Here, x is a variable. So if I specify any value, say a, then you can evaluate f prime of x at a, right? So you can directly calculate f prime of a from the definition, or you can find the general form f prime of x, and then you can evaluate this function at a. Then when I follow the second approach, when I first calculate f prime of x, and then if I want to evaluate that derivative at point A, then we use this notation. This vertical line means you are evaluating this dy dx, df prime, at point A. Sometimes we use this notation instead of the vertical line. In either notation, both implies that you are evaluating the f prime at point A. Now, we say f is differentiable at point A if f prime of A exists. Okay? We say the function f is differentiable on some interval a from a to b if it is differentiable at every number in that interval from a to b. If one of these a or b is an infinite value, like this from a to infinity, that means for any value x greater than a, this function is differentiable. If the function is differentiable on from say negative infinity to a, then that means for any x less than a, the function is differentiable. Now we say, if I just say if function f is differentiable, that means if it is differentiable at every number in its domain. In that case, we say it is just differentiable. And if I do not specify any point or interval, then that means that function will be differentiable at every number in its domain. Now, let us consider example 5, which is quite useful and important example. Where is the function f of x defined by the absolute value of x differentiable? Now, as you know, when x is positive, then this absolute value sign doesn't have any special meaning, and the absolute value of x will be just x. So for any so for positive x, we have this, the absolute value of x will be the same as x. Now for any x, now if I consider very large h, then x plus h, and if h is negative valued, okay, so if x is positive, I have this graph, and when h is large, then x plus h may be on the left, to the left of 0, but when I consider the differentiability of a function, I'm considering the limit of this expression, right, as h goes to 0. So h will be at some point, eventually it will be very small. So without loss of generality, I can assume that h is quite small, so that x minus h is also positive, and x plus h is positive. Okay. So, I mean, depending on the, so, so even when h is a negative value, since I'm considering the limit as h goes to 0, I can assume that x plus h will be positive because I'm considering very small, tiny h, right? So even when your h was large initially, but eventually I'm reducing its value so that x plus h will be quite small. I mean, x plus h will be positive because h will become smaller and smaller. So, so if x is positive, if x is positive, and as h go to 0, x plus h will be also positive. So f prime of x, which is the limit of this average rate of change, and x plus the h will be at some point positive. So we can just remove the absolute value sign, and the absolute value of x plus h will be just x plus h at some point. So So the numerator will be x plus h minus x. So we get just x is canceled and we get h over h. After the cancellation one more time, we get the limited value is 1. Or in other words, when you look at this graph of the function for positive x, you have y equals to x. That is the graph of the function. And every point in this to the right of 0, the slope of the tangent line will be just y equals x itself. That will be the tangent line. So this red one is the tangent line with the slope 1. 1 is the slope of that red line at every point to the right of 0, right? So this slope, right? Slope of the tangent line at every positive number x, okay, is 1. That is the derivative of f at x. For the negative x, we have slightly different situation. To the left of 0, I have this graph because the for negative x, absolute value of x will be negative x. So this is the graph of the function to the left of 0. And when I consider h, and if h is, h is approaching 0, so at some point, x plus h or x minus h will be also within the same, in the left hand side of 0. X plus h will be also 0, will be negative if h is small enough. So absolute value of x plus h will be, for that h value, negative x plus h. So the numerator is now absolute value of x plus h will be negation of x plus h, and the absolute value of x will be also negation of x. So after cancellation, so that numerator will be negative x, negative h, plus x. So after cancellation of negative x and plus x, you get negative h, and after the cancellation of h, you get negative 1. And as I said, when you look at the slope of the tangent line, the slope of the tangent, the red one, is negative 1. So that is consistent with our calculation. So to the left or to the right of 0, my absolute value function is differentiable. Okay? Now, when x is 0, then we have a problem because by definition, if this function is differentiable, f prime of 0 must be defined by the limit of this expression. And when I evaluate my absolute value function as 0, so you get the limit of the absolute value of 0 plus h minus absolute value of 0. Now, absolute value of 0 is 0, right? Now, the problem with is the absolute value of h. So when h is positive, as we observed in the previous slide, when h is positive, the absolute value of h will be plus h. But if h is negative, then the absolute value of h will be negation of h. So that means when I approach 0 from the right, I'm considering the positive h. So absolute value sign just is removed and the limit will be plus 1. But if I approach 0 from the left, my h will be negative valued. So the absolute value sign changes the function value to negative h. So after the cancellation, the f prime will be negative 1. So this is the right hand limit. And this is the left hand limit. And in this example, the right hand limit and left hand limit both exist, but they are not the same, right? So these two are different. That means the limit does not exist, right? So f prime 0 does not exist. So the graph of f prime will be just the plus 1 to the right of 0 and negative 1 to the left of 0. But this function f prime is not defined at 0. Okay? So the domain of f prime will be from negative infinity to 0 and 0 to infinity, but this 0 is not included. And please remember the domain of f, the absolute value function, will be all Fourier line from negative infinity to plus infinity. So the two domains are different. Okay? And this function, the absolute value function, that is differentiable at all real number except 0. Please remember this fact. Okay? And yeah, since time's up, I next section. So the f prime does not exist. Okay, and that is quite clear from the graph of the function, because f prime of 0, if it exists, that must imply the slope of the tangent line. But as you can see, we cannot consider any tangent line for this absolute value function at 0. As I said, the tangent line must touch the graph. Okay? But we cannot find such tangent line at the origin. So no tangent line at 0. Right? Anyway, so we just observed one example of a function which may not be differentiable at certain point. Right? Anyway, let's call it a day here and see you on Wednesday. If you have any questions, please email me. Thank you for listening and see you on Wednesday.